Alright, hell yeah. So we have a football being kicked into some grandstands. And this is not a trivial problem. We need to find the equation of the grandstands as a constraint with the equations of projectiles. And it could be overwhelming. So this problem is cool because I can come up with a solution that's just kind of a guesstimate, and we can kind of graph and get a fairly accurate answer. So I'm going to try to do that as quickly as possible, and then this video kind of goes through the process that I used. So the fast of it is that gravity is 32.2. I realize that this has a velocity of 80. It's going to have an upward component. I'm just going to say close to 64, because this is 64 divides by 32 by 2. So what this says, the acceleration of gravity, if we have 64 feet per second of velocity up, our velocity is going to change or slow down by 32. So after 1 second, this is going to be 32. And then after another second, it's going to be 0. That's going to be the top of our arc. It's going to have 0 vertical velocity. And then another second, it's going to have 32. And then come back down to 64. So it's going to be in... And then right there is super cool, because we can see that it has 4 seconds of hang time. Now the other simple thing about projectile problems, and kind of cool, is that the horizontal component of the velocity never changes. So that's going to be 40 from geometry, and if we have 40 feet per second horizontally and have a hang time of 4 feet, we're going to have 160 feet if the grandstands weren't there. If it's just going up and then coming down to hit the ground. So graphically, I'm going to do that. I'm going to say maybe this is 50, 100. So if that's 50, this is 50, this is... So there you go. We have 150, and it's going to come down right there at 160. Halfway, we know that the halfway point is going to be the top of the arc. Alright, so that's going to happen at 80. Oh yeah, and I kind of totally forgot. The other thing on this is how high is this going to go? How do we figure that out? And that seems like it's going to be complex, but it's actually pretty simple. And it comes down to the fact that this thing has a velocity of 64 feet per second, and it has a velocity at the top of 0. And this is linear, actually. So from 64 to 0, what's the halfway point? 32, and that's going to be the average velocity. So we're going to have 32 feet per second, and it's going to be 2 seconds up. So 2 seconds up. So we're gonna be at a height of 64 feet. So if this is 50 and this is 100, so we're basically kind of just right at that height right there. So I was able to kind of quickly graph this and be like, okay, this is 50, this is 80, this is going to be the top. And I actually just said, hey, let's say the projectile's motion is just kind of linear. So it's linear up to 80 and then linear back down to 160. So this is 160, this is 80, this is 50. And now let's just draw in the grandstands. Grandstands start at 55 feet, and they're going to be at a 45-degree angle. So I'm just going to draw a 45-degree angle. And then hell yeah. And so let's say we're just right there. So let's say we're at 100 feet. Cool. So we know that we're going to hit... and they want to know this distance, so it looks like H is 45 feet. And then maybe you want to know how long it's going to be, what the hang time of this is going to be, how long it's going to be in the air for. Oh, and the other thing is you don't have to make it linear. You could just draw this, and that was the other thing that obviously this is probably more accurate for what it's going to hit. And it's going to hit right there, and I didn't have to kind of fudge my numbers. But hell yeah, let's say we have 110 feet, and it's actually going to hit right there. This is going to be 55 feet. So H is 55 feet. Now how long is it going to be in the air? Maybe you want to know that. Well, that's going to be this 110 feet divided by 40 feet per second, because that's the velocity this direction. So if we have a velocity of 40 feet per second and we're going 110 feet in this direction, that's going to give us the time value. So 110 divided by 40. All right, 110 divided by 40. That's going to give us a time of 2.75 seconds. And so that's it. That's how I was able to estimate this. And the most important thing about a good estimate, I mean, why this was valuable, because this requires the quadratic equation to actually get the answer right. And I don't know, just anytime I use the quadratic, I could be so far off where now, you know, let's say I get an answer of 2 seconds to 4 seconds, and I get this distance of h from 40 to like 70 feet. I know, hey, I'm at least kind of getting close. You know, I might have errors, but this, having a good guess like this is just really helpful when figuring out, like, making, because sometimes I'll make major errors and then I can come back to this and realize, no, I for sure did something wrong. Because even a problem like this, I used gravity as 10 meters per second squared, and I used everything else in feet per second. And I was just like, because I'm just so used to using gravity as 10, I'm not very used to using gravity as 32. But because I did this method, I was able to pick up on that. So anyway, so this is just part 1. I go through the full process and we just make a better graph. Part 2 will be actually solving this using equations. Hell yeah. Alright, hell yeah. So MIT has an open courseware. I'm taking the Engineering Dynamics class. This is an undergraduate class, probably a sophomore year level class. And my motivation is to kind of go through it and then just realize that at such a university, they're going to make things kind of sound more complicated than they need to be. So my objective is to kind of go through and kind of demystify that. So anyway, this was the first problem up, and we're not going to really read through it. You can if you want to, but it's just kind of interesting because they have a concept question. I guess I didn't even put that in here, but they just said, hey, given this setup, we have a velocity of a kicked football. It's at an angle. We just want to know what the component in the x direction is. That was kind of the general gist. And this is a good trigonometry review. And I don't know, you know, if you have a 60-degree triangle, I just know that, well, and you might, so if we have 60 degrees here, this is 60. Just know that you know at least every angle of this right triangle, and this is going to be 90 minus 60, or this is going to be a 30-degree angle. And if you have a 30-degree angle, and you should know that one side is going to be half the hypotenuse. So if here's the hypotenuse, and I just do the hypotenuse with like a, hey, that's going to be the larger number. This is going to be 1/2 of that, so 0.5 maybe times that hypotenuse. Or just 50% of the hypotenuse. Cool. So that was kind of the concept question that they started out with. The other thing when it comes to vectors, especially when you're just kind of like looking at a problem, this 60 degrees, we do have a velocity upward and it's at an angle of 60. Once you get to about 60, you should know that, well, you should know that 45 has equal components vertically and horizontally, and those are going to be about 70% because the sine or cosine of 45 is 0.707. This is a good one. I always memorize this to 3 digits. I think 007, and just know that, you know, it's not going to be like that. It's not going to be this. And it wouldn't be 0.770 because you would just memorize it to 2 decimals. So 0.707, think 007. That's an easy way for me to remember sine, cosine 45 to 3 digits. Anyway, but the reason I bring that up is because if you get past 45, even up to 60, well, let's show the component. So we do have this vertical component, and just from a visual perspective, it's going to be about the same. So let's say this is 80 feet per second. Well, this one looks about 80 feet per second. So even if you just guess that it's like 100%, hey, you're not far off. Because here, what we would have is this vertical component, and we would have sine 60, which is the same thing as cosine 30. And this is 0.866. Another really good one to memorize, 3 decimals. And it has an exact value of square root 2 divided by 2, which makes sense because this is 1.4142 divided by 2. You know what I mean? You got 140 divided by 2. What would that be? I have no idea. No, this isn't that. This is that's going to be this 0.707. Yeah, I'm not as up to speed on knowing these as this is the square root of 3 divided by 2. And the square root of 3 is also a good one to know to 3 decimals. It's 1.7, 1.7 what? I think it's 1.72, and then I think it's like 3, 1.723, and then something where both these add up to 120. So if you want to go that route, I think I maybe have it wrong. I don't think so though. I just don't know. Whoa! So this would be. Oh, this is going to be 48. It's 42 plus 48. 70 plus 50 is 60 plus 60. Hell yeah! So it's kind of a fun one to memorize to 4 digits on this one. 1.7, and then you're just like, what is it? Is it 1.73, 1.72? Well, it's 1.7248. So anyway, all right. So holy hell, what are we going to do for this problem? What I want to do for this problem is to kind of make it simple. Is like the fundamentals of kicking something with a vertical velocity upwards is that we know that that's going to slow down. If you just throw a ball straight up in the air, it has an initial velocity, and then at some point it slows down, it comes to a stop at the highest point, and then it starts to fall back to the earth. And so we want to know why it does that, and we go to our, we just know that it's acceleration, and we have gravity. So gravity is going to be in metric, it's going to be 10 meters per second squared, and for this problem, we're gonna be in feet per second. So this is going to be 32.2 feet per second squared. And it's always good to write this as 32.2 feet per second per second. That means that anything that's going to be thrown up is going to have its velocity change by 32.2 feet per second. That's going to be the change in velocity every second. Now this one, it might be more difficult to do things in feet per second because, I don't know, we don't really think of things in feet per second. We think of things in miles per hour in America, in American units. So yeah, most problems will probably be easier to do in meters per second just because we have, I don't know, probably a more intuitive understanding of what a meter per second is than feet per second. Anyway. All right, and now we're going to go over kind of what this is and kind of what direction it is, because it typically will have a negative sign on it. You know, if we have our coordinate system where this is 0, 0, this is going to be the positive x direction over here, this is going to be the positive y direction up. Acceleration is always down. So what that means is we throw something up at 80 feet per second. After the first second, it's going to be about 30, it's going to change its velocity by 30 feet per second. So it's going to go from, I'm just averaging this as saying 30, right? So we're going to go from 80 to 50. So after 1 second, this ball is going to have a velocity of 50 feet per second. After the next second, it's going to have a velocity of 20 feet per second. Okay, and so on. So this is the first thing that I did with this problem. I was just like, well, this is what I do with all projectile problems. Because I know this relationship, and this is the fundamentals right here. This is the kind of the meat and potatoes of what's happening. It's because gravity is because you have F equals ma, and I should be going over like Kepler's equation right now, not Kepler, but the universal gravitation equation of Newton. But I'm not. But it's just I think we all get that. Hey, gravity is going to be gravity has an acceleration of 32.2 feet per second, and or 10 meters per second. Rewrite it because it gives you kind of a general gist of what that means. It means that if something gets thrown up, its velocity is going to change by that amount every second. Cool. And then so once we get up to 20, in another second, for hella it's going to stop and then go back the other direction. And so even for this problem, I was just like, well, let's say it does like it changes by 40, and now we're going to be going You know, we came up to a stop, came kind of back down to this point, then we go from 20 to 50 back to 80. So it's going to take 1 second to get to here, another second, so 1, 2, 3, 4, 5, and maybe just a little bit more. So 5 point, that was my initial guess, just about 5 seconds. Now we can refine this. So that's the first thing I did. And that was just kind of guessing that the vertical velocity was just going to be 80. But we know that it's going to be 0.866. So here's the next thing that I did. Wasn't too hard. All I did was, well, let's see what I did. Because this is 86%. Like, what's 86.6% of 80 without a calculator? It's like, I don't know. But what I can do is move this decimal to here, and every 10% is going to be 8 feet per second. And so, well, we're going to have 80 of, sorry about that. We're going to have at least 8 of those to get it. This is at least 80%, so we're going to have 8 times 8 is like 64. So that's kind of the next value that I used, because 64, you know, 64 and 32 kind of matched up. So I'm just going to say this vertical velocity was 64 feet per second. And now we're going to go from 64 to 32 to 0, back to 32, back to 64. And this, like, obviously this problem, we're kicking a football into some grandstands. I don't know if you actually read the problem. Like, I typically don't, because it messes up your fundamental understanding of maybe what you know about the fundamentals, and then you're going to use those fundamentals to finally answer a problem. So that's just my method to not really read problems and get to a point where it's just like, even if you come up with your own problem, because your comprehension is bad like mine, do that problem instead, and then maybe go back and be like, well, was that the actual problem they were trying to get to? Anyway, so we have these grandstands, so I'm just going to pretend like those aren't there. And we're just going to say that this thing gets kicked up and then falls back to the ground. The other fundamental of when you have a projectile that goes upward, yeah, gravity is changing its velocity. But when you have a sideways velocity, this thing's going to be going this way at 40 feet per second. There's no Earth over here that's making it accelerate this way. Or there's not another huge mass like a planet over here that when this thing has a velocity this way, it starts to slow down and then come back towards that planet. So the Earth underneath us is what's causing things to go up and down, but it has no effect when we throw like a baseball. In this case, we're kicking a football. Even though we're arcing it up, you know, and it falls back, we understand that. Whatever velocity it has, this component, that'll always stay the same, because there's going to be no change in acceleration. There's going to be no acceleration in this direction, which means that means there's going to be no change in this velocity at any point. Sweet. All right, so that was the second thing that I did. I just changed this to 64. That was a closer approximation. 1, 2 seconds up, 2 seconds down. Cool, so now we have a hang time of 4 seconds. The other thing that I did much later was just, I went to Google and being like, hey, what's the average hang time of a football? And I think it was 4 to 5 seconds. So we're kind of in that window of, like, I think I don't know if it was 3 to 5 seconds or 3 to 4 seconds, but yeah. So we have our first guess was 5 seconds. Our next guess was 4. This is probably closer to what a football's hang time would be. And for this problem, yeah, if you're going to kick it at 50 feet per second with that angle, because it's going to have an upward velocity pretty close to 64 feet per second, you're going to have 4 seconds hang time. And because that was at 80%. 80% of 80, that was going to be that 664. But we actually have 86.6%. So this is just a little bit higher. So hell yeah. So our hang time from here back to the Earth is going to be a little bit more than 4 seconds. Alright, so now the meat and potatoes of this problem, because this problem is not trivial. This is up there with like a ski jumper, you know what I mean, like launching off a ski slope and then landing on some sort of, you know what I mean, a projectile in the air, a skier lands, but as they go this way, this slope falls out from underneath them, and in this case, it's the opposite. As this football is headed towards the stands are going up like this, so the stands, you know, are kind of coming at the football. And that's going to be for part 2 to actually solve this 100%. But I just really wanted to go over how you can get an estimate for this problem. And we're going to do it from a graphical perspective. And, you know, like I think, you know, we're just going to take our time. And I'll probably put, you know, kind of the answer right at the beginning, maybe try to do it in 5 minutes. But yeah, all this is just really good information. So now we're going to take this problem and then just do a graphical representation of it to see if we can get the answer. You know what I mean? This is going to be kind of cool. And this is legit because when you use the algebra and you use the integration or however get your equations and get your unknowns, you're still using geometry. You know what I mean? So we're actually just showing you graphically how to use that geometry. So I'm going to say this is the origin, and that's that point right there. Now we're going to get our x-axis. So this is going to be 10, 20, 30, 40. I'm good with this. 10, 20, 30, 40, 50. And then 60, 70, 80, 90, 100. Oh, and then even from this sheet of paper, cool. We can get one more piece of information. Now I did this, I just kind of forgot to do it right now. So if there is no grandstands in the way, you know the hang time is going to be 4 seconds. So now maybe the question is like, how far did you kick the football? Well, cool. You had a velocity of 40 feet. So your velocity is 40 feet per second. Your hang time's 4 seconds. You know what I mean? And so now this is going to be fairly easy. But again, if you don't know how to multiply or what to divide, what to multiply, because this one's straightforward, we just multiply these two numbers. But sometimes you actually want to find the time and you already know the distance. So what I do is to get your units, so I say this is feet per second, and then over here I have seconds. And then I say, what do I need to do to these to get my distance in feet? If I want feet, well, feet is already upstairs. Seconds is downstairs, seconds is upstairs. So I multiply these, and then the units of seconds goes away, and I'm left with units of feet. So sweet. So I'm going to say 40 times 4, that's going to be 160 feet. Okay, so this is kind of a wild problem because, I don't know, is it drawn to scale? Did they do a pretty good job? Because this is 50 feet, but if the grandstands weren't there, this thing would be going 160 feet. So sweet. So that's what I'm using to draw my graph. All right, hell yeah. So I'm going to go 100, 110, 20, 30, 40, 50. 1, 2, 3, 4. Yeah, so we got 150, 160, 70, 80, 90. Okay, so I'm just going to, so we know that's going to be 160 feet that way. Now this, I'm going to do 10, 20, 30, 40, 50. Oh, now the other question. Yeah, so let's go back to here. Now this one isn't quite as simple, but what I really wanted to show is how to get a guesstimate of how high this thing is going to go. And so here is my technique. Even though like the velocity is going to be like, it might not be, oh no, this is fascinating because sometimes with these problems you don't know what's linear and what's like parabolic. But no, this is totally straight up linear. The velocity is going to start at 64 feet per second. In 1 second, it's going to drop to 32. In another second, it's going to drop to 0. That change in velocity is linear. So this football is going to start with a velocity of 64 feet per second, and then linearly slow down to 0, kind of in the vertical direction. And so now this kind of links the integration, because when you do integrate, you're going to have something like acceleration is 32.2, maybe a negative, and then velocity is going to be negative 32.2 times time plus the initial velocity. And and let's see. Yep. And so if you have an initial velocity of 64, after 1 second, you're going to be negative 32 plus 64. So you're going to have 32 feet per second. After 2 seconds, you're going to have negative 64 plus 64. Your velocity is going to be 0. But this equation is linear. It's just a function of time and the initial velocity. And so even if you didn't know that, you can just go back to this hang time, be like, well, in 4 seconds, like and it's 4 seconds to do the full trajectory. So it's also good to kind of know what the time frame is at the top when it stops, and that's going to be 2 seconds. Okay, hell yeah. And so I guess just to get to it, we have a velocity of 64 feet right at the beginning, a velocity of 0 feet per second right at the top. And so now the question is, what's our average velocity? And it's just halfway between those. So I always break out the example. And this is a good one. Kind of having your playbook. Just because it involves driving and just mentally, let's say you're in the course of 1 hour, you're going to get in your car and you're going to slowly increase your speed to 60 miles per hour. Now, it's nonsensical because no one's going to do that, but mentally you could imagine that. You know what I mean? You're like, okay, I'm going to weirdly do that. But now the question is, like, what's my average speed? And it's just going to be the halfway point. And it's going to be 30 miles per hour. That might be an intuitive thing to kind of have an understanding. Now, from the integration perspective, it's the area under this curve divided by 1 hour. You know what I mean? From that perspective. From the other perspective, it's just the average. If this is your line, it's just the average of this line, which is the integration, which is the area under the curve again. And then I got into a conversation where, yeah, they make this stuff so technical where it's just like, it's so simple just from a simple perspective. But, you would have the integration of the function from here to there, like 0 to 1 hours. That's going to be your a to b. And then we would divide by b minus a. This is the average value. So if this would be the average velocity. If this is a function, if our function is velocity, yeah, it's just kind of interesting. You know what I mean? How, like, you get so technical with it. But that's why I think every time I integrate, typically I'm maybe just trying to find the average value. That's why when you say integration is area under the curve, well, cool, what does that give you? This is in units of miles per hour, and then this is 1 hour. So we would have miles per hour times 1 hour, and you would have distance. So cool. So here, the area under the curve is something. It's distance. But sometimes I'm after just that average value, which is the total distance that we go. That's the area under the curve divided by the time it took to do that. So if we went a total distance, in this case, to find that area, it's a triangle, so it would be 60 times 1 hour times a half because it's a triangle. So that's going to be 30 miles. Cool. So the area under the curve is 30 miles, and the time that we did that divided by 1 hour gets you that 30 miles per hour. All right, hell yeah. So that was kind of my first attempt at showing, you know what I mean, how sometimes when I'm thinking of integration, I'm kind of just thinking of the average value, because I'm getting the area under the curve, but I'm also just dividing it by whatever this parameter was. And that basically gives you that average value. If this is a function of velocity, if this equation is velocity as a function of time, I can integrate it from a time of 0 to 1 hours and divide by 1 hour minus 0 hours. That's going to be the integration from a to b divided by b minus a. But why? I don't know. I mean, I guess every equation has to have, a technical way to explain it. But man, I mean, just such a useful equation, but it just looks too technical. You know what I mean? So that's why it's just kind of nice to have this idea that a lot of times when I'm using the process of integration, I'm interested in the integral divided by the bounds, you know what I mean? Or, you know, even that's too complicated. Usually I'm just trying to find this average value. It started at 0, went to 60. I'm trying to find the average. Now if it went like this, you know what I mean? Obviously we're going to be slower for more time, so our average value is probably going to be a little bit less. You know what I mean? All right, hell yeah. So that was a pretty good. Anyway, so what were we trying to do? We know that our hang time to the top is 2 seconds, and we're going to have an average velocity of 32. Let's say 32 feet per second. And so we have 32 feet per second and 2 seconds. Like, cool. What do we want to find? We want to find. I don't even know what we want to find. Oh, we just wanted to know the total. We wanted to know the height it got. Yeah, I was really interested because I was trying to make my graph. It's like, how high is this thing going? I'm kind of curious. And, you know what I mean? So we have that, again, we have that initial speed of 64 feet per second, 0 feet per second at the top. That means we have an average speed of 32 feet per second for 2 seconds. I think it does just trip you out because it's kind of hard, like, you know, we're so used to like driving horizontally and figuring out that distance. That vertical distances seem kind of tricky. You know what I mean? So let's just turn this horizontal. Okay, I'm going to go 32 feet per second for 2 seconds. Oh, okay. I went 64 feet. For whatever reason, like saying it that way was like a light bulb went on. But yeah, vertical speeds and vertical distances are just a little bit tricky. But now back to our graph. We know that our highest point is going to be 64 feet. Okay, hell yeah. So we can write that in. 10, 20, 30, 40, 50. And then we have 60, 70. I'm going to go all the way up to 70. 64 is going to be pretty close. Okay, and then so, and the whole reason I'm going over this video is because you're going to come across problems, and this problem actually is probably way too hard for even just a lot of college students, because if you don't know the trick to this problem, I don't know how you're going to stumble across the trick. You know what I mean? Where you figure out this stands is a line, and this line, you are using geometry, and you're trying to and you're like, hey, and it actually intersects your coordinate system, and you know, this is your continuity, this is your constraint, where if you hit like this, this distance in the x has to match up with intercepting this the equation of this grandstand, and anyway, I don't even want to go because even mentally it's hard for. I know how to do it. I just even mentally have a hard time even saying what's going on. But I just thought this was so cool that even I could do this process and get a general idea of where this thing is going to hit the grandstands and how long it's going to be in the air. Those two things just really fascinated me. And the distance is going to be this way. So that's exactly what they want. They want to know the distance this way into the grandstands that it hits, and the grandstands are at a 45-degree angle, so this distance is the same thing as the height of the grandstands that it's hit. Alright, sweet. So we can totally set this up with geometry. Okay, so we know that the highest height is going to be 64 feet, so we got, you know, somewhere kind of right in here. Make a little line. Alright, back to this. We knew we had air time of 4 seconds. We have a speed of 40 feet per second. We're going to go a distance of 160 feet. So let's write that in right here. And then what we know about projectiles, as long as there's no wind or anything else, we're going to be going up and then down. Because this velocity is the same, it's going to be symmetric. So if this is 160 over here, I'm going to go to 80, which is right here. And this point right here is going to be the top of my arc. Okay, hell yeah. And even from this, so now I'm just going to do this piecewise, and I'm going to come back to this, because like, what do we draw in here? I'm going to explain that in a second. So let's go back to geometry. These grandstands start at 55 feet. This is 60, this is 55. So right here, these grandstands go up at a 45-degree angle. So it's really nice to have graph paper. I didn't do this with graph paper, and I actually got a fairly close answer. Because when we do this, again, we're gonna have this equation. You're gonna have continuity. It's gonna be a quadratic. You're gonna have to find the time that it's gonna be in the air before impact. That's how I solve it. Find the time that it's gonna be in the air, and then figure out like what its position is using that time. And so because it's a quadratic, your answer might be, I mean, it might give you a 14 seconds in the air, you know, and you're just like, maybe that's not right. You know, so what this does, using geometry, gives you a check on reality, and it's fairly accurate, and it's kind of cool. Okay, so here's the grandstands, so we got those going, and now you can see that, hey, whoa, this problem's coming together. I mean, because we said it was going to land at 160, and I was just like, this doesn't even look to scale. If this is 60 feet, 55 feet right there, 160 would be way off the page. But now we can see this thing is so tall that even at the top of its height, it's already at 60, 70, 80. It's already at 80 feet this direction. Okay, so now here's going to be the secret sauce, because this is where you don't have to get too hung up. Because now I'm going to go, what's the path of this projectile? And I am literally just going to do a straight line. So that's how I did this problem, just from a guess perspective. You know, anytime you even like have quadratics and stuff, I don't know, you can make it linear. Your answer is going to be wrong, but at least it gives you a strong guess. You know what I mean? So right here, this is going to be a linear guess of the football. And check it out. It looks like it hits right there. And so we got an answer. So it looks like at this is 110, 105. So let's say 103 feet it hits. They want to know what this distance is. So I do 103 minus 55. Don't know what that is, but 100 minus 55. Ooh, I don't even know what that is. 100 minus 60 is 40. So we're going to have 45. And 45 plus 3. So we got 48. So H is going to be 48. And booyah. And then actually, and that was good enough for me. And we can even from here, now we can actually figure out the time in the air. How do we do that? Well, we know the horizontal velocity is always going to be 40 feet per second. And so our horizontal distance is 103. So we have 103 feet. And we have 40 feet per second. This is exactly one of those scenarios where if you're not sure what to multiply and divide, this is a good strategy. Write out your units. We have feet per second, and then over here we have feet. What do we do to both of these to get seconds? Well, we can recognize that seconds is downstairs. And so if we multiply straight across, well, seconds will still be downstairs, and we'll have feet squared. So obviously that's not what we want to do. And to get something from downstairs to upstairs, we divide by it. So we're gonna go feet. We're gonna go feet divided by this feet per second. So feets cancel, and then the seconds pops upstairs. That's what we're gonna do. So we're gonna say the distance in feet is 103 feet divided by 40 feet per second, and this is gonna give us the time in the air. So let me break out a calculator. Alright, hell yeah. So we have 103 divided by 40. So this gives us a time of 2.6 seconds. And that's very valuable. So the whole reason I'm doing this is because when you actually use the equations, try to find the constraints, try to get right answers, you can always come back to this to check reality. You can be like, hey, did we hit a distance of 103 feet? Were we about 2.6 seconds in the air? And so I went through that whole process, and then while I was doing that, I was just like, oh, well, no duh, we can still, like geometry, we can still come in here and know that this thing, we can actually just kind of follow the path that it would take. And so that's kind of what well, let's do this. Okay, hell yeah. So this is the path that it would take, kind of a parabolic path. And so this would give me 100 and, let's say this is 110, 15, 112. So let's say we have 112 feet. Minus 55. So this distance is going to be 57. So heck yeah. So just right off the bat, I kind of knew that this distance maybe between 40 to 60, and so that's going to be kind of my window to hit in the grandstand. So I mean, just right there is just like, hey, we're not bad. 50 to 60. So we're going to be, the football is going to hit the grandstand somewhere between 50 to 60 feet. So that's an incredibly accurate guess just by using, we didn't use any equations. We just used the fact that we have a vertical velocity that's going to decrease and then start increasing back to hitting the ground. And then just doing a picture of that path, and then put the grandstands right in the way. And then you are going to intercept that. And so 112 feet divided by 40 feet per second. This is going to give us the time. So 112 divided by 40. And we have a time of 2.8 seconds. So I'm going to say, hey, that's probably a more accurate answer. And that's it. So this whole process gives us, we're going to say 112 feet is when it's going to, that's the horizontal distance. H is going to be 57 feet. And I'm hoping that's fairly accurate. And, I'm not going to actually double check my answers from doing the problem. That's going to be part 2. But it was just kind of cool. And, I'm just satisfied that physics problems can have these guess, the ways to just kind of, intuitively get to the answer, kind of from a simple perspective. And they're very useful for double checking right answers once you get deep into the equations and the constraints. There's just so many places to make little errors. Anytime the quadratic equation comes up, I can't get it right the first time. There's so many sign negatives in there that I'm just not very good at it, that if I'm doing anything with quadratic, I feel like I must have to have a second way to double check my answer. So hell yeah, so this has been it. And it was just kind of cool because these problems are not trivial. When you have projectile motion and something's hitting, in this case, a grandstand. Also, you could have the same thing again of like a skier jumping off a slope and then the slope is falling away. And, a cool problem for that would be have the slope change angles. So then if you actually got past a certain point, then you would actually land on a steeper part of the ski run, and then you would have to figure out, well, where you actually are. That would be kind of a cool problem. But and a problem like that, you could still do it graphically. You could figure out your horizontal distance, your time in the air, your average velocities, and then your distance, your vertical distance. So that's what we did for this. All right, hell yeah. So thanks for joining me, and guess what? That's a video.